The universe keeps a chemical receipt for its first minutes. Every galaxy carries that record in starlight, split into thin spectral lines. Those lines tell how much hydrogen, helium, and lithium exist. One element refuses to match the script, and the mismatch keeps growing. In old, metal-poor stars, early chemistry should stay nearly untouched. Their atmospheres act like time capsules from far earlier cosmic eras. When astronomers read their spectra, hydrogen and helium behave. Lithium does not, even in stars with the least heavy elements. Lithium looks simple, yet it acts like a trapdoor. It carries 3 protons, which makes its spectral signature easy to tag. This same element powers common rechargeable batteries on Earth right now. In space, its faint fingerprints set off alarms. Rewind cosmic expansion to its first seconds and matter turns into a hot soup. Temperatures sit near 18 trillion degrees Fahrenheit, far above any star core. Nuclei cannot hold together at first. Within minutes, cooling lets the first light elements begin to lock in. Then the numbers get ugly. Calculations say a tiny dose of lithium must survive that early furnace. Telescopes look for it in the oldest stars. The count comes back low, again and again. Where did the missing lithium go? This early universe picture rests on more than one clue. The cosmic microwave background fills the sky with a faint afterglow. Its temperature map pins down how much ordinary matter exists. With that input, equations predict light element ratios with tight limits, including lithium. Hydrogen should dominate by mass, near 3/4. Helium should follow near 1/4, made during those first minutes. Across galaxies, those ratios line up with spectra from gas and stars. That agreement is why the lithium mismatch stings. It breaks an otherwise clean pattern. Lithium forms as rare side products in the early nuclear chain. A proton and neutron make deuterium, then helium builds fast. Lithium appears in trace amounts, on the order of parts per 10 billion by mass. That tiny fraction still should be visible in very old stars. Astronomers test these predictions far from the Milky Way. Light from remote quasars passes through thin intergalactic gas, leaving absorption lines behind. Those lines reveal hydrogen and deuterium levels consistent with early universe math. This makes lithium feel like one wrong tile in a finished floor. The lithium count is near 3 times lower than expected. Worse, a second isotope shows up far too often. Lithium-6 should be scarce, yet it appears at levels that defy early universe nuclear rates. 2 mismatches, 1 element. That is not a rounding error. Most early lithium should be lithium-7 with 4 neutrons. Lithium-6 with 3 neutrons is fragile and hard to make in the early furnace. The expected ratio is near 2 in every 100,000 nuclei. Observations hint at far more lithium-6 than that. Reading lithium relies on narrow lines near the red part of visible light. A spectrograph spreads starlight into thousands of wavelength bins. Tiny dips mark where lithium absorbs. Those dips are faint, and they sit near other lines that can confuse the reading. Small biases can matter. A strange consistency shows up in many ancient dwarf stars. Their lithium level stays nearly flat across a range of temperatures and compositions. That plateau hints at a shared origin, set before these stars formed. Yet the plateau sits below the predicted value. The universe keeps repeating the same low answer. Gas clouds between galaxies offer another route. When a quasar shines through, each element stamps a pattern on the beam. In theory, lithium lines in these clouds would bypass stellar effects. In practice, the clouds are faint, the lines are weaker, and the results remain uncertain. What if lithium is not missing at all? What if stars hide it? Lithium burns at about 4.5 million degrees Fahrenheit, far cooler than a star core. If surface material mixes downward, lithium can vanish from the atmosphere. That would fool every spectrum. In many stars, convection churns like boiling water. Material from the surface sinks, warms, then rises again. If that circulation reaches hot layers, lithium nuclei break apart. The surface then looks lithium poor, even when the star started rich. Mixing depth becomes the key unknown. Rotation and magnetic fields can change that mixing. Faster spin can stir surface layers into deeper zones. Slow spin can let heavy elements sink through diffusion over billions of years. Either way, the lithium line in the spectrum can drop. Yet the near-uniform plateau stays hard to explain with mixing alone. Lithium-6 may come from a different factory. High-energy cosmic rays slam into carbon, nitrogen, and oxygen in interstellar gas. Those impacts can shatter nuclei into lighter pieces, including lithium-6. That process runs for billions of years. It can raise lithium-6 without fixing the missing lithium-7. This turns the lithium issue into a balancing act. Early universe math sets an initial lithium-7 level. Stars may destroy part of it after formation. Cosmic rays may add lithium-6 over time. Each step is plausible alone, yet the combined story must match every spectrum across the sky. A deeper fix would alter early universe nuclear reactions. New decay events in the first minutes could break beryllium into lithium differently. A change like that must leave deuterium and helium untouched. Few tweaks can do that. One wrong move ruins the rest of the element ledger. The microwave background locks down ordinary matter density. Deuterium in intergalactic gas gives a second anchor point. Helium from ancient gas regions adds a third check. Any new early universe process must satisfy all three. That constraint box is tight, which is why lithium keeps resisting clean explanations. Observational bias remains a live suspect. Lithium lines form in thin stellar atmospheres where temperature varies with height. Three-dimensional atmosphere calculations can shift the inferred abundance. Small blends from nearby lines can mimic lithium-6. Fixing those details demands higher resolution spectra and better calibration across many stars. Lithium may hide in dust grains within gas clouds. Elements can stick to solid particles, then drop out of the gas phase that spectra sample. If early gas lost lithium to dust, stars formed from that gas would start lithium poor. That idea fits some regions, yet dust behavior varies widely across environments. Lithium is not the only chemical headache in astronomy. Heavy elements like gold and platinum need rare cataclysms to form. Their totals in galaxies push event rate estimates to the edge. Light elements do the same from the opposite side. Each mismatch points back to the same question: what really happened early on? A single clean test could settle much of this. A firm lithium reading in pristine intergalactic gas would dodge stellar mixing. Yet the line is faint, and it sits where noise loves to hide. The next set of spectra may settle it, or it may deepen the crack. New instruments can gather more photons from dim targets. Higher signal strength can separate lithium from nearby blends. Wider surveys can sample thousands of halo stars, not dozens. With that scale, patterns in temperature, age, and motion can reveal whether stars destroyed lithium or whether the early universe estimate needs revision. Laboratory nuclear physics matters here too. Reaction rates for beryllium-7 and helium-3 set lithium yields. Small shifts in cross-sections can change the predicted lithium level. Those rates come from accelerators and detectors on Earth. Better lab limits narrow the space for any hidden fix. This problem is not remote from daily life. Every atom of lithium in a battery traces back to cosmic nuclear reactions. The same element, in a faint stellar line, tests the first minutes of cosmic time. If lithium is wrong, the earliest timeline needs rechecking. That reaches into every later chapter. For now, two paths stay open. One path says stars hide or destroy more lithium than expected. The other path says early universe nuclear history has missing steps. Each path predicts new patterns in future surveys. The element is small, yet the stakes span the entire cosmic origin story. Across a universe tens of billions of light-years wide, a light metal keeps refusing to fit. Hydrogen and helium agree with early universe math with impressive consistency. Lithium keeps slipping through the net. When that mismatch yields, it will refine how the first minutes are reconstructed. Until then, the inconvenient element stays in the spotlight.